Alrighty, let's go ahead and get started. Let's do this. So thank you so much for choosing to attend this session. I know there were a lot of options, but thanks for prioritizing this one. So my name is Robin. Here today in this session, we'll be discussing detecting website intrusion and account compromise with machine learning. So this is a quick overview of everything that we'll be covering today. So we'll start by giving you an introduction into machine learning and giving you all of the background you need to know. Then we'll get into data and features, and so how do we take our raw application and or infrastructure logs and make good model inputs from that, and we call those features. Then we'll discuss model management, so how do we train, test, and deploy models for these use cases? How do we validate that they work? And then how should our applications and infrastructure work with them, whether in a real time or in an asynchronous environment? And then finally, we'll discuss how we utilize model outputs, and we'll go through a handful of case studies and discussion on trends and what we're seeing. So let's start off. An introduction to machine learning. So artificial intelligence and machine learning are two words that are generally thrown around and combined together a lot, but they're actually separate. So AI, or artificial intelligence, is the broader concept of enabling a machine or a system or an algorithm to sense, reason, act, or detect like a human. And machine learning is a specific application of AI that allows those machines or systems or algorithms to extract knowledge from that data and learn from it autonomously. So there are two cases that you might want to consider a machine learning-based detection versus a traditional detection. And so one of them is you are trying to search for something that is not payload or signature-based. If you can do that and you have a hash or a regex or something like that in mind that you can use, that's great, but you don't need machine learning to do that. And the second case that you should consider is behavioral-based detection, and not just any behavioral-based detection. Generally, behavioral-based detections that cover a broad amount of features and or activities that you would like to aggregate together. So machine learning in particular is really good at learning normal behavior patterns and activities, provided that you give it good input. And so in our experience, it's been extremely effective for creating different detections and getting broad coverage. We have reviewed at this point many billions of events. We have responded to hundreds of users in our enterprise use cases, and we found that the architectures and everything that we'll be describing provides a really effective prioritization for effective response as well. And so with that, let's go on ahead and get started. So these are the three different types of machine learning that we'll be talking about today. And so we'll be sticking to traditional machine learning algorithms. So no large language models here, sorry to disappoint. And so in the supervised learning space, this is generally what you'll think about when you consider a traditional machine learning-based detection. So these are the majority of your algorithms. And you generally assume that you need a well-labeled input. And so in this case, we would want our behavioral profiles or our aggregations to correspond to the true positive status for an incident. But in most cases, you won't be able to start with that unless you have a really spectacular security operations center that has done all those aggregations and features for you. And more importantly, in the supervised learning case, generally you need many, many examples to the tune of thousands of data points that you can learn from. And so in most cases, you won't have that. So we actually have to start with unsupervised learning. And so this is where we just have unlabeled data. And so we are just looking at inputs, and we are trying to analyze where things deviate from the norm through a variety of algorithms. And then after we have a few examples of labeled data, we can pivot to a semi-supervised use case where we have a mix of labeled and unlabeled data. And so in this particular case with semi-supervised learning, we generally have a smaller subset of data needed than what we would need to create a very high quality supervised learning model that could stand on its own. So in this case, we mix our labeled data with our unlabeled. And so the general rule of thumb, like I mentioned, is we'll start with unsupervised learning. It will have the worst performance of the three types here, but there are some techniques that we'll discuss here shortly on how we can improve performance. Then you move into semi-supervised learning after you've gathered some labeled data, and so I like to do that through adversary emulation. And then finally, your ultimate goal is to go to a supervised learning model. But you can always start from something. And so with that, let's talk about data and features. So what actually goes into a model, and how do we decide, most importantly, what goes into a model? And so we always start with our threat models and our TTPs. And so in particular, when you're deciding on TTPs and things that you would like to detect on, if you're creating a single model, your TTPs and the scopes of your coverage and what you're trying to build the model for should generally be within the same domain and functionality. So if you threat model your application and you have a few threats around direct authentication into that application, so working with an on-premises like authentication solution, you have threats around SSO authentication, and then you also have concerns about malicious file upload on your application. So the first two would be great TTPs to combine together to create a unified model, and I actually recommend that. We find there's a lot of really interesting signals from both. But in that third case, for the malicious file upload, that's a completely separate domain, and it will just be too many features for the model to handle generally. Like, you should have a very grounded domain in what you're trying to detect. You can't just throw the kitchen sink at the model and expect it to have good output. And so after you've enumerated your TTPs, you have to take a look at your available data. And so there's almost always going to be some sort of data you're missing, or that the data you thought you were logging isn't actually what was being logged. And then the overlap between the TTPs and available data are what you can create your model on. And so on the available data, you'll want to make sure that you're taking a look at both your upstream log sources and your downstream log sources. And so in particular, if you have any authorization services where their logs are separate from your application, for example, or infrastructure, you'd want to make sure to incorporate those. So when we go and do this in our cases, we're combining anywhere in the neighborhood of like 3 to 6 different data sources in order to create all the aggregations and get all of the data that we care about. And then finally, when we're considering our available data, we also need to make sure that we're filtering and getting that meaningful data. So for example, if your website has a browser pop-up or like a banner that loads automatically on load, the user isn't necessarily directly interacting with that application or with that particular endpoint, even if it's getting loaded and logged like they are. And so keep that sort of in mind when you're considering your application logs as well. Make sure that you are actually reflecting the logs and the behaviors that the users themselves are initiating. And so if we zoom out a little bit, how does this fit in with the overall development lifecycle for machine learning? And so like I mentioned, we always start with our threat modeling and our TTP enumeration. The other important thing that we need to do is we need to engage our incident detection and response team fairly early on. So a fairly common requirement that comes up is the detection and response team needs to know why something is being flagged. And so if that is a requirement in your case, it's important to understand that early on, specifically because when you get to the build and test phase, the model architectures that you can use are limited as a result. So for example, only certain model architectures will give you feature importances. And if that's something you need to surface, know that early on. Your next phase, and arguably where you'll spend most of your time, is in the development phase, specifically in the data domain. So you'll understand your logs. You may annotate them as appropriate. So if you have 20 different error logs that go in, you may need to cut those down and get that down to 5 or 10, or group them together as appropriate. And then that goes through our process called feature engineering, where we create our aggregations as well. After we've created all of the possible feature combinations we may want to consider, we go through the feature selection process. So we generally don't want to send in 200 or 300 model inputs. We should select down from there and make sure that our features are unique and additive to the model and helping it make decisions. Then we get into model development. So this is where you actually stand up your AI infrastructure and train the model. You might try a few architectures here and a few different techniques. And then we have to test it and make sure it works. So generally, adversary emulation and synthetic data that I'll detail here shortly. And then finally, you get into your staging environment and/or a small-scale user test, where you go through A/B testing and you ensure that your model outputs are as expected and you're validating your response plan. And then if you have any sort of threshold in what should be escalated to your incident response team, you'll validate that here as well. And then finally, you can enjoy the fruits of your labor. And if you're doing this right, you are creating model input, you are logging model inputs, they are mapped to TTPs, and you have a status associated with them. And so then you can particularly start to put together a source of threat intelligence for your teams to consume. We found a lot of interest in this step as well, even if they aren't directly integrating with the detection models. So let's talk about the feature types in more detail. And so like I mentioned, these are pretty simple model types. These aren't LLMs, so we have to give the models a way to understand our text features. And so we'll start on the right hand, the rightmost arrow. And so specifically when you're dealing with text features, there's a lot of good inputs there. So think like your model or your URL parameters, your JSON inputs, and we need to give the model a way to understand those features. And so we do that through creating an embedding. And so that's basically an array of numbers that translates our words and characters into that array of numbers. And so we need that for the model to understand it. It cannot understand text by itself. And in the next case, we have a categorical variable. And so this is a slightly separate way to understand text inputs. So there are three different types of categorical variables. We have a nominal variable, and so in this case, think, for example, we have an application logs where there's a bunch of different events getting logged, but three that come to mind are an authentication event, a page load event, and maybe a form submission event. So those might get encoded and translated into numeric values that represent each event. So say 5, 13, and 17. No particular rhyme or reason to those those values, but the model needs a way to understand that 17 equals this particular event. The next case that you'll want to consider is an ordinal variable. And so this is where, very similar to a nominal variable where we have those inputs, but in this particular case, those numbers have a meaning and a relationship to each other. So with an ordinal variable, if you have threat intelligence for an IP address that says this is low, medium, or high risk, those might get to be translated into the numbers 1, 2, and 3. And so those represent different levels, and they are related to each other. And then finally, you have the classic Boolean variable. So this is your flag feature. So has this IP address or this user been involved in a security investigation before? True or false, 1 or 0. And then finally, you have your classic numeric variables. So think your floating point numbers and your integer values. Nothing super special there, but we do usually end up having a number of these features, and those usually comprise the most. And so with that, let's go through a super detailed example. So let's say in this case, we are starting to build a model for an authentication system. We want this model to work in real time. And so our particular threats and the things that we're trying to consider are user enumeration threats and password brute forcing attacks. And so this is an example of what your data might look like when you first start out and take a look and pull these logs. So a few things immediately come to mind. What do we see? We see some null values. And so on our leftmost column, those are the actual column names and what we're pulling from our databases. The middle values are our counts along with the null statuses, and then the rightmost column has our object types. And so we'll handle them all differently. But immediately, the first thing that comes to mind is we have 0 non-null values for a number of these features. And so that means this data is straight up missing. In our databases, it's a null value, and we can't use it. The other important thing that we notice is we are doing this data exploration in a Python library called Pandas. And when we introspect into this data, we might have some non-null values for the client interfaces, for example, but they're all logged as the same string value, which also doesn't help us because the model can't use the same value to make a decision one way or the other because it's all the same. Let's also talk about what we're not seeing in these particular logs. So in particular, we're not seeing any sort of IP address or session cookie associated with this activity. And so the general rule of thumb is you'll want multiple identifiers to aggregate over. So that way you can give a much more complete timeline and behavioral profile to the threat intelligence team and to your incident responders. So for example, if we are aggregating just over a particular user and we see that this user has had 15 invalid password submissions over the past hour, that might be high, but that alone right there isn't worth it to escalate to an incident response team unless you have very strong feelings. But if we put that together with our IP address and our session data, and we say the IP address has attempted to authenticate and has resulted in 50 user does not exist errors over the past hour, they're associated with 20% more request volume than the next highest, and they're also associated with 500 password submissions over the previous day, then that tells a very different story compared to just that one user. And so you'll want to surface both when responding to your threat intelligence team, because that tells you not only is this user doing something suspicious, but it also looks like the device that they're coming from is part of a broader attack. And so our next step is to augment our data sources. So in this case, we discovered that our error logs were in another table, and so the columns here are the same, but here in the middle column, we can see that our counts of our values, A, are non-null now, but B are higher than in our previous slide. And so we've done that because we've unioned, in this case, the email addresses because we're intending to respond to users. So we have a higher count. So that means there are some cases where these users have never been associated with a presumably successful authentication event. And so we can also see here that this second table has had a number of additional details. So one is the inclusion of our IP address. And then the second case, you'll notice a number of these columns here are very detailed. And so these are called derived columns. And so these are columns where we have pulled out those different error types and those, from those error logs. And then we've created a count per the specific cast event time. And so we'll need both the cast event time and these particular counts, so that way we can perform the aggregations in our last step. And so this is a sample of our final last set of features and the final amount of data and what we're considering. So you'll note that we are keeping our identifiers the same, but you'll notice a few things. So one is prior to the aggregations over the time periods that we'll discuss in a second, we've done some filtering. So if there are service accounts or accounts being used by automation in your case, we've filtered those out. Generally, we found that those have very different behavioral profiles than your base kind of users who are interacting with your web application on an expected basis. And then the second thing here are the time periods. And so the time period that we see that we go back the furthest in this particular case is 7 days. But the value that you pick for your application should be directly related to your users and their behavior patterns. So for example, if you have a finance application where your users primarily authenticate in at the end of the month so they can deal with month close, quarter close, year close, that sort of thing, you'll want to take a look back over that broader time period. And then the general rule of thumb, I didn't do it here so you can get a good example of how we're really aggregating over everything in a number of different identifiers. But you'll follow an I over 2DK. So in that finance example, if we're following that, our first time period would be 15 days, our first time period would be 30 days, next time period 15, then 7, 3, etc. And then the final time period that you choose will be directly related to how often you intend for this detection to run. So if you are intending this to run in real time, you'll want to go down to that roughly 1 hour granularity. If not, if you're running this once a day in an asynchronous sort of environment, you can go down to that 1 day granularity and save yourself some of the feature aggregation and compute time there. The other important thing to note here is this is a lot of features. Should you actually use all these features? And you should almost never use each and every one of these features, and so that is generally because a lot of these values will be highly correlated. And so generally when these features are correlated, that means they follow the same sort of value, or the same sort of pattern, rather. So as one increases, the other increases, or there could be negative correlation, whereas one increases, the other decreases. But generally, you don't want to include highly correlated features because they're not adding to the model. There's an expected pattern that we can already understand from them. So generally, you'll want to select those out unless you have a particular reason for keeping them in, for example, weighting and detecting more strongly or more likely on a particular TTP. Additionally, if you have other features or too many features to use for your environment, you'll use also your TTP prioritization. So if you have 20 TTPs related to your authentication system, but you have 5 low priority ones, you can cut those if you're just dealing with too many TTPs or features related to them on the order of like many hundreds. And then finally, don't disregard your intuition when going through this process. Generally, you have a good idea of what features are related to the kind of attacks that you're seeing and or what kind of logs are related. If you don't think that they're related, don't throw the kitchen sink at the model and expect it to have good output. Make sure you're not disregarding your logic here as well. And so with that, we'll do a quick recap here and then we'll get into model management. So in the short term, understand what data your websites and infrastructure have available. Identify your candidates for ML-based detections. In the longer term, identify gaps in your existing logs and then begin remediating them. That'll usually require working with your application or infrastructure teams. Then identify your relevant TTPs and begin your feature development. So let's talk model management. And we'll start with model architectures. And so I like to use a technique called ensembling. And so that's where we actually take 2 models, and then in this case, both models have to agree that something is an anomaly for us to actually consider it as an anomaly. So we found this naturally reduces a number of the escalations that we create. And so in particular, I like to use 2 types of architectures. And so the examples given here are for an unsupervised case, because this is where most of y'all will be starting. So I like to use an isolation forest, and so that's our tree-based model. Our tree-based models will give us feature importances, and in most architectures that I've seen, you can actually enumerate the decision tree, or at least part of the decision trees, so you can really understand quite deeply why something was being escalated. And then, of course, you have your local outlier factor model, and so roughly this will give you the quantify, or it will allow you to quantify like how anomalous this activity is. So the rule of thumb there is the bigger the number, the more anomalous. And so specifically, both of them have to agree. And then what I also like to do is I like to scale the local outlier factor value to be a floating point number between 0 and 1. So generally, as you get closer to 0, the more normal that value is, and then the closer you get to 1, the more anomalous that value is. And so even if something is an anomaly, that doesn't mean that we have to engage an incident responder. Generally, the more anomalous that behavior is, the stronger that we would like to respond. And so I'll give you a few examples here in a little bit on what the strength of response might look like. So let's talk, we have our data, we've trained our model, but how do we actually validate that it works? And so this is generally the order that I like to go in. So we will start with our synthetic data. And so what that looks like is we have our TTPs, and then we map specifically which features map to those particular TTPs. So first we create a base payload where all of those features that we have are set to the average values that we have pulled from our logs over all of the time periods. Then we can begin testing per TTP. So we can spread those values generally from the average, and then we'll go 1 standard deviation beyond the average, and then we'll see what the model output looks like from there. 2 standard deviations from that average, and then see how the model output looks, and that will allow us to measure the model's coverage specifically for those TTPs and like the anomaly level. The next phase that I like to go through is adversary emulation. And so this is specifically where we try to engage our red team or our purple team to work with us and directly attack our applications or infrastructure, so that way we can gather labeled data. And so the way that we like to do that, you'll see the architecture here on the right-hand side. So we have the way the purple team works at Meta is a little bit special, where they create not only the attacks for us, but they also give us automation to continuously rerun them. So our automation and our payloads live in an AWS account and in an S3 bucket, and then those payloads get pulled onto an EC2 instance where we can directly run those TTPs against our applications and on our model. And so what that allows us to do is validate that our aggregations are working as expected. So if we run a password reset request or a password reset automation 10 times on a particular IP address, we expect that to come through, and we perform that validation there. In particular, so in a real-time case, we have an internal service called FB Learner that's very similar to AWS SageMaker, and so we have our model deployed there, and so it allows us to deploy a model as a real-time endpoint and then also offline, and we can send it inputs through like a data pipeline. And then finally, after we've done our adversary emulation, you may want to do some form of retraining. And your retraining will be directly related, again, to your user patterns and your behavior patterns. So think on that finance application space, you may want to retrain monthly, and then if you have a higher use application, you may want to retrain even daily. And generally with these architectures, they're not super heavy, so you can generally accomplish that. And then you'll want to make sure that you're testing on retraining, and so we'll pull from both our synthetic data and our adversary created data if needed to go and understand and make sure that our model is still detecting as expected. So assuming you've gone through this process and you're happy with how your model is doing, how do we actually get this to integrate with our applications and or infrastructures? So the first option that we have is a batch job. And so with a batch job, this is something that is running asynchronously, and so it's not actually interacting with your applications or infrastructure in real time. You might be writing to a security investigations queue and or an output table that your applications or infrastructure can pull from should they desire it. And so it'll follow the same general process that we've described already, where you have your application logs, you do your transformations, and then you can throw it into a model and determine what's considered an anomaly. In this particular case, we have a feedback loop, and we're going through our security investigations process, where they can label things as benign or true positives in this case. And we can use that to, again, begin gathering that labeled data and hopefully begin pursuing a semi-supervised model case once we have enough. So there are a few benefits to this and a few drawbacks. So on the benefits side, we can generally get through a number of inputs in a very short amount of time. Most modern data infrastructure and AI infrastructure will let you get through many millions in usually about 45 minutes, or a few 100,000 in about 10 minutes. And so that's pretty good. And so batch is a great option if you're not convinced yet that you want to bother your infrastructure or application teams with this detection. Also, redeployment here is very easy. Since you're not working with an application or infrastructure team directly, you can swap out these models, and generally there won't be any sort of direct user impact, but the only folks who might notice are your security investigators. And so on the downsides, of course, it's not real time, so we can't respond in real time. This would be some sort of asynchronous, like after the fact. You could get pretty close to real time, but generally you can't take any sort of dynamic response on your applications or infrastructure. And then, of course, in this case, we are also only writing to some sort of output table or incident queue for management as well. So the second option, and where we hopefully like to get to, is an online deployment. And so in this case, we are taking our model from just being a detection to also being a protection. Because the model can respond with inputs, and then your application can respond dynamically as well based on those inputs. So your response, if you have a threshold at 0.6 to be considered an anomaly for these outputs, your response at 0.65 can look very different from your response at 0.95. At 0.65 in an authentication system, you might throw in an extra two-factor challenge when they're doing some sort of sensitive operation post-login. But at the 0.95 case, you could deny login altogether and disable their user accounts. And so in this particular case, though, on the drawbacks, it is much more difficult from an engineering perspective to implement and integrate. So usually in this particular example, we're dealing with a web application, but we have to have some sort of way that we are logging and actively aggregating that user activity, and so that's usually done through a cache. So that way we can send that cached data to the model in order to run those inference events. Then the model can respond with the output, and the application or infrastructure can do as it wants. But what we also like to do in particular, and what we found very effective, is our web application can also prompt the users for action as well. So think like how Google will send you like, hey, was this you when you log in from a new device on your applications? You can do something very similar here, where if the user does respond and says, no, I don't recognize this, that can be a labeled data point that we can then use in our security investigations and response queue, where the user says, no, I don't recognize this, and we have anomalous activity. Let's escalate this to the top for response and or user disabling if needed. And so again, this follows the same general feedback loop, but the addition, in some cases, we'll have the addition of user feedback as well, depending on how we've architected this. The other drawback for this approach, generally if you have high latency concerns, this does introduce a lot of updating the cache, writing to the cache, drawing from the cache, and then an extra round-trip API call into, for example, your authentication system or whatever activity you're trying to deploy on. And then, of course, as you retrain, just know that it will have direct impacts on your users, assuming you are dynamically responding. And so let's talk about the case studies and how we interpret the model output. So this is what our dashboard looked like after running a red team or an adversary operation on our application. And so in this particular case, we are surfacing our identifiers, so our user ID and IP address. But then the other two most important columns that we should talk through are the risky level and the top risky features. So on the risky level, we have low, medium, or high, and so we assign a general rough grouping or level associated with this behavior. And so that can be done through a threshold and or a percentage-based approach. And then we also have roughly the percentile of the score. And so in this case, this was in the top 0.01% of risky behavior for this application. And so we can see, I'm hoping you can see the column names in a little bit more detail. But we can see that it looks like there were multiple features per IP address and per user ID in particular. And so it looks like that this IP address had was starting to enumerate a bunch of different users. It looks like it found a valid user, and it was then trying to password brute force on this particular endpoint. And so this is generally what we like to do because we are giving the incident responders our identifiers, so that way they know what actions they should be taking like particularly against. And then the features, so why something was escalated. And so you will need to update and work with your incident responders quite a bit so that way they can understand the risky features and what everything means. and make sure that you have things documented appropriately. And so in our next case, so very similar columns, but slightly different TTPs that we're hitting. And so again, in this particular case, assuming that you are training and testing your model as expected, you'll want to make sure that you are hitting multiple TTPs and not just like one or two in particular. But in this case, we're seeing multiple TTPs as well. So we're seeing this IP address is associated with a bunch of other suspicious behavior by calls. And then we're seeing a mismatch in our user ID and email address-based features, which could indicate some sort of request tampering. The other important thing here is you can also escalate based on the time periods that your features are associated with. So in this particular case, it looks like we have high counts for features that are specifically related to the last hour. And so we might say that we should prioritize this for response first, generally because we can potentially take preventative action now and prevent widespread compromise. And so in general, a few trends in what we're noticing are anomaly cases are associated with 15 times the number of request errors compared to inlier cases. Anomaly cases are associated with 3 times the number of devices and in terms of IPs and what we're seeing. Anomaly cases are also associated with 5 times the number of cookies. And so in general, out of all of the data that we've seen, anomaly cases represent only about 4% of all our data, with critical being only around 0.1%. And so we found that this has really allowed us to balance extra friction with security. And so quick recap on the modeling side. In the short term, understand which types of ML would be helpful for your data and for your use case. Longer term, develop a testing and integration plan. If you need to work with your application or infrastructure teams to implement something like this, engage them now. And then also work with your security investigators on what would be helpful information to surface. Longer term, begin modeling in your feature experimentation, and then assess your model performance and plan out your adversary emulation. So a few acknowledgements before I go. So I am up here alone, but I certainly didn't build all of this on my own. We'll start with the Enterprise Foundations team at Meta. And so they were the first team that sponsored an ML-based detection and specifically sought this out for a finance-based application, which is why that came up a lot in our examples. Xiaoke and Ryan are our enterprise engineers, Jack, our data scientist, and Yaguang, our data engineer, with Jacob, their manager. At this point, they have consistently staffed this effort now for over 2 years, and so this has been a long time coming. The next folks that I want to thank are the Enterprise Products Applied Research team, and so these are ML engineers. And so we started off with 1 model, but at this point we are up to 6. And so I can't manage those all on my own, and so shout out to Josh, Pratibha, Ziyu, and Henry. They've really taken the time to get to know the security domain and understand what we're flagging and what we're trying to do. And then, of course, a few folks in cross-meta security, Asit, a security engineer, and Justin, his manager. So they were the first folks to bring this on to our incident detection and response team. Yan, our software engineer, who built out our response queue and surfaced all of our relevant information. Jason Lee, so a little bit over a year ago, I was mentioning that I should probably submit some of this work to a conference, and he was like, well, you should really be aiming for something like RSA. So shout out to Jason, I'm here today. And then, of course, Jason Grace, a Purple team lead here at Meta, who's helped build out the adversary emulation process for machine learning. And so with that, I will go ahead and take questions.
If anyone has any questions, can you guys line up at one of the mic stands up there?
Thanks for the great presentation. Is the mic on?
No, it doesn't sound like it.
You may just need to step closer to it. It was doing that last session too, sorry.
Oh, okay. How about now? Oh, yeah.
Yeah, we're good.
Thanks for the very interesting presentation. I'm curious, in your online deployment model, where you're getting high-quality labels from like the security response team, do you have any thoughts about how to like increase the importance of those labels when they go back in your training data set?
Yeah, so it's really around curating the training data set where you're balancing the number. So in like the semi-supervised case in particular, you can use techniques around like upsampling that data for the supervised cases. And then specifically what I also like to do is something called label spreading. So in that case, the model architecture will actually look for data points that follow a similar behavioral pattern. And so it'll say, hey, if it's similar to this and this is already labeled, it strongly considers that as well.
Cool. Yeah, thank you.
Yeah, thank you. It was a nice session. We have to do the same procedure right from step 1 to whatever you have explained every time for every use case, or we can learn from previous use case and try to build or reuse some elements from the previous use case.
Yeah, so generally what I do is you will have to go through the whole process, but it's generally accelerated. So what that looks like is you might have your set of features already pre-aggregated for like your SSO authentication, for example, and then if you're trying to use it for another application that supports both, you can just pull those and specifically the features that are already non-correlated for you, and then your feature selection is generally over a smaller domain, so we found it to be much faster.
Thank you.
Hello, thank you for great presentation. So I have 2 questions if possible.
Mhm.
So the first one is regarding the performance assessment of the model once it's in the production. So how can you define the retraining strategies or the frequency of retraining the model based on which metric? And the second question is for the adversarial emulation. So what kind of adversarial emulations that you are performing or in the team they are performing?
Yeah, so on the retraining, I generally try to optimize for AUC, so like area under the curve and that sort of thing. And then on the adversary emulation, could you repeat the question?
I mean, I would like more elaboration from your side on how they're emulated, because the model is already in production, so how?
No, so that's that's done before the model hits full production. And so generally what that looks like is you'll run a red team operation against your application. And so in most red team operations, we have to provide particular TTPs that we want them to test. And so they're guided and kind of bounded by that. So it's generally different than like a full traditional red team operation where they try and hit everything. So generally our red team operations are more limited.
I see. And after that, you fix the model if there are some kind of issues. Okay.
Right, yeah. And so that's generally the phase where we've noticed like most of the issues like that I called out with the aggregation. So like it's tricky like with SQL and with our SQL builder. So like we like to validate and make sure we're aggregating as expected.
Thank you so much.
It's a great presentation. In terms of data generation, have you thought about, I know you said you're not going to talk about LLMs. Have you thought about using LLMs for generating some of your data? Because I noticed you're doing data introspection and all that.
Yeah, I mean, honestly, we haven't, mostly because it's not grounded in like our user behavior patterns. And so that's why we've leaned more on the synthetic data side. Like we can get the LLMs to generate random numbers and output for us, but it's not particularly meaningful. In general, it might be helpful if we provided like some of the boundaries within the LLM. So like we could provide a range and have it generate for a particular count or a feature, and that might be helpful. But it's just not something that we found particularly helpful because so many of like the LLMs hallucinate and will just disregard the required output schema.
What about data cleanup?
Data cleanup. So the LLMs themselves, generally, at least the ones that we have at Meta, aren't executing the code on our behalf. Like we have a bunch of pre-built libraries that help us do the data cleanup side at this point, and so we've usually just used that, and we have functions specifically around removing correlated features already.
Okay, thank you.
Do we have any more questions? Are you going to be available? Will you be on site at all
Yeah.
for the rest of the week? Do you have any other like meetup times, or if people want to meet up with you, do you have anything available?
Yep. Yeah, I will be outside here in like the atrium area for about an hour, and then I'll be here like all tomorrow and Wednesday if you guys want to say hi or have any other questions. Cool. If that's it, then.
Awesome. Thank you so much.